quiet.
Yeah.
Okay, ladies and gentlemen, I'm going to spend 2 minutes on chemical bonds. Chapters 8 and 9 are about bonding. Here is all of Chemistry 1's ideas in 37 seconds. A chemical bond is a force of attraction that holds a group of atoms together and makes them function as a unit. There are 3 types of bonds that we are interested in. The first type is an ionic bond. An ionic bond is characterized by a complete transfer of electrons between atoms. It involves a metal and a non-metal. It comes about because there's a strong attraction between the positive and negative ions that make up an ionic bond. The formulas are usually given in the simplest, lowest ratio, the empirical formula. They are usually crystalline solids at room temperature. They have very high melting points. Right, now, moving on to covalent bonding. Covalent bonding is a sharing of electrons between atoms. It's a non-metal and a non-metal, or a non-metal and a metalloid. The formulas are usually given in their true ratio, so it's a molecular formula. They usually have low melting points, and a covalently bonded molecule may be in any state of matter at room temperature. A metallic bond, I'm talking about one type of metal. The atoms in one type of metal is characterized by a sea of electrons surrounding positively charged centers. What this means is the nucleus are stationary; they cannot move, but the electrons can jump around, and it's this. Yeah, they're delocalized. Thank you. The delocalization of these electrons makes them conduct electricity. It's attraction between the metal ions and the electrons. The formula is actually just the way you see it on the periodic table. It has a range of melting points depending on the number of valence electrons, and they are solids. Okay, this is fodder for the test, which will be next Tuesday, which is the day before Thanksgiving break begins.
We only have 2 days next week?
You can show up any day you want. Okay, now you're on film doing that. Okay, ladies and gentlemen, let's talk in depth about bonding. A bond is a force that holds a group of atoms together and makes them function as a unit. The type of force that we're talking about is electrostatic. An electrostatic force is one based on a charge difference. Bond energy is the amount of energy required to break the bond. Remember when we were figuring out the enthalpy change in a reaction? This was the bond energy chart was the weirdo one that was reactants minus products. That bond energies that you were given was the amount of energy you need to put into the bond in order to break it. The bond energy is based on Coulomb's law. Who knows Coulomb's law? I do. Okay, the bond energy is equal to a constant times the charge of the first ion or atom times the charge of the second ion or atom, and the distance between the centers of the atoms.
What's that first thing?
This is constant K.
Oh, okay.
So what?
That looks very similar to the gravity.
It is exactly the same. Nice call.
Wasn't R
It's the
squared?
same as Newton's law of universal gravity.
Well, I thought it was R squared.
Is it R
Newton's law.
squared?
Huh?
R squared?
It must be, huh? But it's not. Because it is in his law. Okay. I need to look it up because I bet you it is R squared. I think I have a typo. Why do atoms bond? Atoms bond because they achieve a lower energy state, lower potential energy, when bonded together than they do when they exist apart. And remember, the universe is lazy, and so it likes the lowest possible potential energy. So, in other words, the atoms are more stable when they're bonded than they are apart. So an ionic bond is an electrostatic attraction between ions, the reaction between a metal and a nonmetal. One atom completely transfers electrons to another. Okay, the bond, and you know what I need to talk about here? All of this you need to keep in mind what I'm talking about. I'm talking about the link between two atoms or two ions. Or, I'm not talking about the molecule itself. I'm just talking about the thing that's linking together either two atoms or two ions. Are you clear? Because you will get this confused, and I will be here to say, I told you so. Okay, each bond has a characteristic length, and that length is the distance between the atoms that we're talking about, where the repulsion of the electrons to the other electrons and the repulsion of one nucleus to the other nucleus is minimized between the two atoms. Here, look. All right, so here we have a hydrogen ion with this proton and its electron cloud, and a neighboring hydrogen ion proton and its electron cloud. And they're so far apart they have absolutely no interaction. You bring them closer together and the electron clouds come within the same vicinity and they're starting to irritate each other. There is repulsion of the electron cloud from this one and the electron cloud from this one. There's also some repulsion of the two nuclei. But they finally settle a distance apart from each other where the attraction of this electron to this proton overcomes the repulsion of the two electron clouds. This will be the optimal distance, and the distance between them will be the bond length. A covalent bond is one in which the electrons are shared between two atoms. It results from the mutual attraction of the two nuclei for shared electrons. Now, there are two types of covalent bonds. The first type of covalent bond is called a nonpolar covalent bond. And you know what? A lot of times people drop the nonpolar. If it just says covalent, you are to assume it's nonpolar covalent. That's where there are equal sharing of electrons. Let's go back to this hydrogen. Hydrogen has the electron configuration 1s1. So here we'll depict this hydrogen's valence electron. It meets up with another hydrogen which also has an electron configuration of 1s1. We will depict its electron as an X. When they share, when they combine together to form a covalent bond, they both benefit from the shared electron and they both gain noble gas configuration. They share their respective electrons absolutely equally. One is not tugging them towards itself. If you were to think of it as a region of space, it would be exactly in the middle. It's a nonpolar covalent. Now, a polar covalent is a bond in which one nucleus has a greater attraction for the electron than the other. That would be unequal sharing. That would be a hydrogen bonding with a fluorine. Fluorine has 7 valence electrons. Now, fluorine is really, really attractive to this valence electron of hydrogen. What happens is, if you were to think of it as a region of space, then the electron would be closer to the fluorine than it would be to the hydrogen. That would be polar covalent bond. Electronegativity, you recall from last week, is the ability of an atom in a molecule to attract shared electrons to itself. They figured out when they noticed there was a difference in actual bond energy and the expected bond energy, it was discovered that some electrons are tugged to the nucleus more tightly. Fluorine is the most electronegative, and that's the way you can abbreviate electronegativity. Because it has the greatest effective nuclear charge for its size and is very, very attractive to electrons. The Zeph for fluorine is +7. It only has 2 energy levels. So the proton, the nucleus is closer to the valence electrons in fluorine than any other halogen. So it is really tugging onto its electrons tightly, and it's trying to coerce another electron to it. Francium is the least electronegativity because it has a huge atomic radius, and its Zeph is equal to +1. All right, remember that francium has 1 valence electron, and between the 1 valence electron and the nucleus are 86 core electrons. So it really doesn't care about that outer electron. Okay, this is what I need you to remember about the difference in electronegativity and the type of bond. If the difference in electronegativity is 0, then the bond type is covalent. Remember, boy, that is not focused. That's better. That is non-polar covalent. If there is an intermediate or a middle type of difference in electronegativity, then it is polar covalent. That would mean one of the electrons is being hogged by one of the atoms. If there is a large difference in electronegativity, that means one of the atoms stole the electron. It means one of the electrons was transferred from the metal to the non-metal. Okay? Please get out your electronegativity chart. All right. Good news, bad news. Which would you like first?
Bad news.
Bad news. Oh, he said, where is helium? It is not on this chart. We don't talk about electronegativities for the noble gases because they don't care. Why do they not care?
Because they're already there.
They already have a full lot of
Just making sure everybody knows that.
Thank you. Okay, not third grade. Yes. Okay, we are not. So here's the good news. I will let you use this. Here's the bad news. On the AP test, they do not give you the chart. What you have to do is rank electronegativities based on the most electronegative and the least electronegative. So it's proximity to the most or it's proximity to the least. To determine the electronegativity difference between 2 atoms, you would do this. Delta En is equal to the absolute value of the 2 atoms that we're talking about being bonded together. Let's take our, let's take S and O. I don't know. You okay? 2.5 minus 3.5 gives us an absolute value of 1.0. That difference in electronegativity will tell us, based on a score, whether it is nonpolar covalent, polar covalent, and ionic. So a score of 1 puts it in the polar covalent region. Now, I do want to talk about the spectrum of covalent, non-covalent. We don't talk about this. There is no, in real life, there is no cutoff point. There is no way when there's a little gate right here and says, oh, anything from this point on is non-polar covalent. Anything from this point is polar covalent. It's a continuum. As you go this direction along the differences in electronegativity, it becomes more and more ionic in character. So far, so good. We reserve the term ionic for a nonmetal and a metal. We reserve the term covalent for two nonmetals. So if we would look at the difference in electronegativity between these two atoms, we know this is by far the most electronegative atom on the periodic table. It has a value of 4. What's hydrogen? 2.1? 2.1. So the difference is equal to 1.9. 1.9, according to this, should be ionic. We're going to call it very polar covalent because it's two nonmetals. Get it? Crickets?
Yes.
Thank you very much. Thank you very much. Okay. Now, bond polarity, the hogging of an electron by one member of the bonding party, gives rise to something called a dipole moment. Do not be afraid. A dipole moment is no different than you in 3rd grade drawing Mickey Mouse ears when you drew water. If these are the hydrogens have a plus charge while the oxygen has a minus charge. That, you didn't know it at the time, is a dipole moment. When a molecule, water, has a charge distribution where there's a positive and a negative end, here's the positive end, here's the negative end, the bond is, it is called dipolar, and the molecule has a dipole moment. Now, let's talk about what's happening to our water molecule. Our water molecule can be drawn like this, right? Did I or did I not tell you that the change in electronegativity was just talking about two atoms linked together? Yeah? So the change in electronegativity is the which one of these atoms, the H or the O, has a bigger pull on the electron. It turns out that O does. That's why it has a slight negative charge while the H has a slight positive charge. It's the same thing with this. When we're talking about the electronegativity difference between this hydrogen and oxygen. So oxygen has the negative part and the hydrogens have the positive part. Do you get that? Mm-hmm. Now, if I asked you what the, I can't do it off the top. Yes, I can. If I asked you off the top of my head what the change in electronegativity would be for this, would you go screaming into the night?
Probably.
No, because you would think, oh, I bet you it's an N hooked to, I just need the electronegativity difference of one of them because they are the same. The same. Okay, now back to our HF. We know that when H and F are bonded together, there is a bigger tug on the electrons from the fluorine, so it gives a negative charge to that side of the molecule. leaving a positive side to this side of the molecule. That is called a dipole moment. And the way you write a dipole moment is you draw a line and the arrow faces the negative end. You write the cross line, and the cross line is near the positive end. And then you use these symbols to denote whether the end has a slightly positive charge or a slightly negative charge. That symbol is the lowercase sigma. You know, the uppercase sigma is that's the lowercase sigma. And it's just by convention that we use sigma to reflect the charge and what side it is. All right, now, since you are really good at this, I would like you to write the dipole moment for this oxygen and hydrogen in a water molecule. Ready, set, go. Got it? Sherry, let me do. Okay, keep going. Are you done? Are you done? Let me see. His is almost perfect. What's he lacking? The sigmas. Well, you look really smart if you write those on your paper. Nobody knows what they are except you and a few other folks.
I'm going to use some as variables.
Okay, I practice really hard to be able to do that. Okay, you can tell by electron configurations how atoms will want to bond. Let's look at, I don't know. Look, calcium and oxygen. Calcium has the electron configuration argon 4s2. Oxygen has the electron configuration helium 2s2, 2p4. These are the valence electrons because they're in the highest principal quantum number for calcium. It is very ready and willing and able to get rid of those two electrons. When it does, it then has the noble gas configuration of argon. When oxygen accepts in the transfer of these two electrons, it then has the noble gas configuration of argon as well. That is the pushing force, the reason why these would like to bond in the ratio that they do. Okay. Now when we have two nonmetals reacting to form a covalent bond, they share electrons so that their electron configurations are in noble gas configuration also. When we do that, we generally draw a Lewis dot diagram where we make dots or some other character for the valence electrons. Remember that hydrogen has 1, where fluorine has 7 valence electrons. When they bond together, they do so that hydrogen now has its outer octet, its outer valence electrons filled, 2 in its S. And then fluorine has its octet of electrons. They are both happy with that configuration. Okay, we talked about this last week really quickly. When a cation is formed from an atom, it loses an electron. And so it has a misbalance, an imbalance between the protons are greater than the electrons. That means that the electrons are being tractor beamed into the nucleus with a greater charge, and so it makes a smaller ion. An anion is the opposite case. There are fewer protons than there are electrons, so the electrons are not closely held by the nucleus. All right, isoelectric ions, I defined that for you last week as well. I want you to know that ions are formed in order to attain a noble gas configuration. Oxygen would be 1s2, 2s2, 2p6, oops, I got carried away, 2p4, 2p4. Now, when it forms an ion, it gains 2 electrons, which makes it 1s2, 2s2, 2p6, which gives it noble gas configuration. If you did the the electron configuration for all of these atoms, you would see they all have the same number of electrons, which means they're isoelectric ions. Okay. Lattice energy is the change that takes place when separated gaseous elements are packed together to form an ionic solid. It's also known as the energy released when an ionic solid forms. Okay, this shows up as a AP question in nothing more than definition form. Please note it says separated gaseous elements, ionic solid. The energy change, the energy released when the solid forms from its ion. It has a negative sign because the energy is released when the bonds are formed. It's a state function. You can use Hess's law to determine the amount of energy release. Okay. Once again, this looks suspiciously like the gravity formula. Now, people will ask, oh, I don't want to do this one, so we'll just do 3. It takes too long. Rank from the smallest lattice energy to the highest lattice energy for the following. Well, the lattice energy is equal to a constant. Let's recall the constant will be the same for all 3 of these, so we can just say the difference in the lattice energy will have to do with the charges of the ions over the radius of the ion. So far, so good? Let's do it like this. Magnesium ion has a +2 charge, and chlorine has a -1 charge. Magnesium has a +2 charge, oxygen has a -2 charge, lithium +1, bromine -1. So if we were just going by charges, this would have the highest lattice energy, is that correct? Yes, this is the charge of the 2 ions. 2 times 2 would be greater than 2 times 1 or 1 times 1.
So it's the absolute value. It's not.
Okay, so now I need to look at the ions. Well, all of these are going to get smaller, right? But this one starts out smaller than this one, yeah? Okay, so this has the smallest denominator. And these are about equal. The charge will override the denominator. So when we look at this, the smallest lattice energy would be the lithium bromide because of the small charge. And then the second one would be the magnesium chloride, once again because of the smallest charge. And the biggest lattice energy would be formed, would be given off when these 2 make an ionic bond. So to rank them small, medium, large. Good? Well, if not good, done.